Okay. Transmission lines. Talk about characteristic impedance, SWR, feed point matching again. Uh, Difference between open and shorted feed lines. Uh, Comparing coax to open wire. Velocity factor, electrical length, and dielectrics. So characteristic impedance of a transmission line is defined at the impedance you see uh, looking into the line if it's infinitely long. So if you terminate the line in its characteristic impedance, you don't see any reflections. It acts as a perfect transmission line, except there's a little bit of loss along the way. The formula for calculating the characteristic impedance is ZO is equal to the square root of the ratio of the inductance to the capacitance of the transmission line. Uh, there's no real reason to figure that out for coax unless you're a manufacturer. But if you're doing something like microstrip on a PC board, that's where you need that formula because you have to figure out the thickness and the width and the dielectric, which is all part of that formula. So if I have parallel conductors, the formula is a little bit different and you don't need to remember it, but it's down there that 276 divided by the square root of the permittivity constant times the log of the diameter to the distance between centers to the conductor radius. So as you see, the distance between centers is on the top. So the larger that is, the higher the impedance is going to be. The radius of the conductor, as that increases, it's going to decrease the inductance. So that's part of that thing about if you increase the diameter of the conductor, how it affects it. That's one of the effects. But the capacitance also increases as the surface area, so it's more like the square. So one of the typical parallel transmission lines is called window line. And it's plastic, kind of like old TV twin lead, except it's about an inch wide, or I guess some of us maybe a half, 3/4 inch. They're around 450 ohms, and the plastic separator has square holes cut in it, which is why they looks like windows. It's a little bit different than ladder line, which just has separators and it's much farther apart. That's usually about 600 ohms. If it's coax, the formula is similar but different. And typically, you're going to see 50 or 75 ohm cable. I don't know that they make 35 anymore. Apparently, back in the olden days, I guess it was Bell AT&T, 35 ohms was better for power transmission, was lower loss. So it was another compromise to come up with 50 because 75 was cheaper and they used it for TV. So 50 turns out to be the mean of the squares of the whatever of the two. So if you take 35 and 75 and you figure out the median of it, it's around 50. So that's how we got stuck with 50. Which of the following factors determine the characteristic impedance of a parallel conductor feed line? Okay, excuse me, 30 ohms. I thought it was 35. So if you can actually work that out, you come out about 50 ohms. Uh, Antennas, we talked about half-wave dipoles are approximately 72. Quarter-wave verticals are 35. You look at off-center fed, there's 200. Um, Folded dipoles are 300. So they're all over the place. End feds are maybe 5,000. There's basically two types of dielectric that are used in coax. It can be a solid like a PVC type or polyethylene, or a foam. The foam has a higher velocity factor. It has a lower voltage limit, can arc over at a lower voltage. And it also has lower loss. So your best cable as far as loss is going to be with a foam dielectric uh, in a solid type coax. The air insulated hardline is probably the best, very expensive and hard to deal with. And just have little separators to keep the center conductor from shorting out. But essentially, it's just air dielectric. Which of the following is a significant difference between foam dielectric coaxial cable and solid dielectric, assuming all other parameters are the same? It's number two.
All of the above. Yeah.
Second one.
Pretty amazing.
What? Lower voltage, lower loss, higher velocity factor. I don't know, was that on the previous chart?
Yeah. Same two.
It's the second, all the above.
Second, all the above the Oh, you have to do it about.
Oh yeah, higher velocity factor. Thought it was there. Okay, attenuation or loss. There's a chart showing various types of coax from RG174, RG58, 8X, 213, RG6, 11, and these 9914 and 9913s, which I think are mil-spec numbers, so I don't know what they're actually equivalent to. And it shows how the loss goes up in all of them with frequency. The bigger diameter cables with foam dielectric have less loss per 100 feet than the smaller diameter, like RG174, which is like 1/8 inch cable. So it's 2 dB loss at a megahertz for 100 feet.
How does the dielectric affect the loss? Does it have to do with like capacitance or something?
Yeah, the dielectric definitely affects the capacitance. And the electric field interacts with the dielectric, and I guess there's power loss in the dielectric. And we can see up here well, your typical RG11 is down to 2 dB at a megahertz. It's 5.6 at a gigahertz. And this 9913, whatever that is down to 4.5. Dan, you familiar with 9913?
The loss is pretty low, right?
Yeah, I don't know. I kind of wondered why this chart didn't include like LMR 400 or none of the stuff seems to have it. I guess maybe it's, I don't know. It's very popular. It's not cheap. It's about $2 a foot. Yeah. 600 is even better. I'm not sure what it is. It's probably $3 or $4 a foot. Let's see. And we express loss in dB per 100 feet typically when we compare them. So I guess you know the answer to this one. So what happens is frequency increases, the loss increases.
Vader patterns.
Yeah. Damn it. I definitely got to fix my mouse. Okay. SWR. I thought this was really cool. You like that? And you can actually, because when Gary and I were talking to Neil last week, he wanted to know what standing wave ratio was. And I found this afterwards, and it actually shows why it's called a standing wave, because you notice the black line isn't moving. Okay.
Oh, I see what you mean.
We're transmitting on the blue line. Okay. It's being reflected back on the red line. And the sum of those gives the standing wave. So it's always, at the same point. It's not moving forward or reverse. And that's causing heating in the dielectric. Of course, in this case, you got like 100% reflection. Huh?
That's what somebody you can drive a pebble in the bottle.
Yeah.
You can see there.
So the SWR is, one way to do it, besides there's other formula of reflection coefficient, is just the ratio of the two impedances. So if it's 75 versus 50, it's 1.5 SWR. If it's 50 to 35, it's 1.4. If it's 50-50, it's 1-to-1, which is what you want. Hard to get there. But I've seen 1.05. Let's see. So if the transmission line is lossy, the high SCR is going to increase the loss because reflection is going to lose power on the way back and back again. And it keeps reflecting until it's totally dissipated. Also, if you got a high SWR and you're looking at your SWR meter that's down at the transmitter, what it's reading is going to be less than what the SWR really is because of loss in the cable. And the worse the loss is, the more off it's going to be.
SWR, if you had a meter at the
Antenna would be what the antenna sees,
yeah,
right?
and that's really what you.
Yeah.
Well, the one on the radio is what the radio.
Right. That's what it cares about because it likes the finals to stay working. Yeah. And transistor finals don't like high SWRs. Let's see. So it's just a measure of the impedance matching of the loads. We've talked about all that stuff. Probably don't need that chart. What's the effect of transmission line loss on SWR measured at the input to the line? We just talked about that.
Transmitter side.
Yeah, we're at the transmitter end, looking into the feed line, measuring SWR. I mean, if I had a high enough loss cable, I could have an SWR 1-to-1. Wouldn't get anything in the antenna.
What's your estimate?
SWR would be good. Transmitter would like it. What's the relationship between high standing wave ratio and transmission line loss? Bravo. What standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load? In other words, I got a 200 ohm dummy load. It's the ratio. Alpha. What standing wave ratio results from connecting 50 ohm feed to a 10 ohm resistive load? It's a tricky one. Yeah. They tried to fool you with 1-to-5 because the ratio is 1-to-5, but you always go with the high number. What's one reason to use an impedance matching transformer at a transmitter output? I like she. Yeah.
Well,
Like to keep my power supply ripple low.
Trying to minimize that out.
If the SWR antenna feed line is 5-to-1 and a matching network at the transmitter end is adjusted to present a 1-to-1 SWR, what's the resulting SWR on the feed line?
Trying to figure out what they're asking.
I think they're trying to trick you.
Yes, they are. This is not blowing up the channel. Say trouble.
I think you do have to make an assumption, because it doesn't say in the question, but you have to make an assumption on what the characteristic of impedance of the feed line is.
Well, not really. It says if the SWR on the antenna feed line is 5-to-1, what's the resulting SWR on the feed line? you didn't change it.
Yeah, they add all this crap over in there.
Yes. That's to see if you're paying attention.
That measure and transmitter that fixed the problem really doesn't.
Right. I think that's the point.
Wordy answers there. I figured it had to be one of those.
I think the point there is you've got a bad match and you tune it to 1-to-1, it's still a bad 5-to-1 match.
Doesn't fix anything.
Right. Well, it makes the transmitter happy.
It makes the transmitter happy, but it didn't fix the antenna
Right.
or feed line.
Right. And now, if they'd asked what it was on the input to the matching network, then it was 1-to-1. But they said the feed line.
Bill Kerrigan used to say, did you know Bill? Okay, he taught the classes several years ago. He taught mine. He said, a tuner is like putting lipstick on a pig. It's still a pig.
Yep. And it doesn't tune a thing.
A tune spot. Unless the tuner's at the antenna.
Okay. So for matching networks, we can have an LC network. We can have a quarter wave transmission line transformer we talked about before. We use balance and ununs. The difference is a balun is a balance to unbalanced, and unun is unbalanced to unbalanced. Basically, we're trying to prevent a standing wave by matching the impedance of the feed line to the feed point of the antenna. So what causes reflected power at an antenna's feed point? What must be done to prevent standing waves on a feed line connected to an antenna? Okay, matching using coax. So I can use an 1/8 wavelength piece of coax, and I can make it inductive if I short it on one end. I can make it appear capacitive if I short it or if I leave it open on the other end. So depending on what I'm trying to do, I can either make it a capacitor or an inductor. So I take that little stub and put it on there to match whatever this impedance is out here. So I've got a minus J25, which means it's capacitive. So I use a shorted stub, so it's inductive, and I adjust it so that I get a 25 ohm inductive reactance that cancel out the 25 ohm capacitive reactance. And everybody's happy, and it looks like 50 ohms down the line. What impedance does a 1/8 wavelength transmission line present to a generator when the line is shorted at the far end? Of course, this only works for one frequency or a very narrow frequency band. It's not not broadband. What impedance does an 1/8 wavelength transmission line present to a generator when the line is open at the far end? Okay. I can also use a quarter wave length of line, which we talked about before. And here it's going to either give me a high or low impedance, depending whether it's open or shorted. So if it's open, it looks like a low impedance because you get just the opposite. If I have a high impedance at the open end, then it looks like essentially a short or low impedance at the source. If I short the other end, then it looks like a high impedance going into it. Because you look at it, look at the sine wave. If you go 90 degrees, quarter wave for voltage, okay, then I go from 0 to 90, from 0 volts to high voltage. If it's open. I go open to shorted. Okay. Okay. If I have a piece of transmission line that's one wavelength long, and we look at it at 3 points, quarter wave, half wave, three-quarter wave. All right, you're going to see that waveform on it, right? And it appears from an impedance standpoint to go from high to low to high to low as you go along the line. And that's all you're doing with a quarter wave length of line for a particular frequency. It just basically gives you the opposite. If it's a half wavelength, we're like, 180 degrees. So if it's shorted on one end, it looks like it's shorted on the front end. Because you got the same zero voltage and zero voltage. So what impedance does a quarter wave transmission line present to an RF generator when the line is shorted at the far end? Yep. What impedance does a quarter wave transmission line present to a generator when the line is open at the far end?
No.
What impedance does a half wave length of transmission line present to a generator when it's shorted at the far end? Bravo. Okay. Feed line loss. We typically use coaxial cable because it's cheaper. It's easy to use. It's harder to deal with parallel feed line, particularly things like ladder line. Not all antenna tuners have outputs to connect to things like ladder line or window line. I have a really old Dentron that does all the above. But I don't know that they make them like that anymore. It's got knobs. It's got knobs.
A big tuner for the kilowatt has got outputs like for everything.
Yeah.
Plus about 4 coaxial
outputs. So all the open wire type lines are much lower loss than coaxial cable. So for long distances or higher frequencies, it's better to use ladder line, although I don't see ladder line used at VHF or UHF, although it would be better. But usually when you start getting up there, you go to a hardline coax to get air dielectric. How does parallel conductor transmission line compare to coaxial cable with a plastic dielectric? I think it's another red herring. Okay, velocity factor is just the ratio of the velocity of the wave in the transmission line divided by the velocity in free space, or the speed of light. And that gives, it's a function of the permittivity of the dielectric. So the higher the permittivity, the lower the velocity factor is going to be. If I look at that formula, right? Because I increase K, VF becomes smaller, right? Which means it appears electrically longer.
Velocity factor to be high.
If the velocity factor was 1, then it would travel at the speed of light. And the physical length would be the same as the electrical length. Usually the electrical length is longer than the physical length because of the velocity factor. For solid polyethylene, you typically see about 0.66. For foam, 0.8. For air insulated, parallel or open wire, it's like 0.98. So there's very little slowdown in parallel. So what's the velocity factor of a transmission line? You say Charlie or Delta?
I said Charlie, then meant Delta.
Okay. You didn't like Bravo?
No,
Okay. Which of the following has the biggest effect on the velocity factor of a transmission line?
Charlie.
Let's see. And we just talked about the physical length is going to be shorter than the electrical length. There's the formula again. It's the ratio of the velocity to the speed of light, or 1 over the square root of the permittivity constant. So what is the physical length of a coaxial cable transmission? Why is the physical length shorter than its electrical length? What's the approximate physical length of an air-insulated parallel conductor transmission line that is electrically 1/2 wavelength long at 14.10 megahertz? Calculator.
Not even will reach for the calculator.
Okay. Take a guess.
Well, yeah, you don't really, you see, half wavelength on 14 meters, so half wavelength is 7.05 meters for half wavelength long, and we know that the velocity factor for air insulated is 0.98, right?
Yeah.
So it's gonna be close to 7.
Yeah.
It's almost there. Alpha.
I believe you're right.
Well, half a wavelength at 20 meters is 10 meters.
Oh, I said 14.
Yeah, you saw the megahertz there and divided it. Yeah.
Yeah, so it's gonna be.
Charlie. And they anticipated that mistake.
Yes, they did. They do that a lot. So Yeah, that just doesn't seem right.
Two. Is it two?
There's no.
If it's a half wavelength long electrically. Well, let's see, when I worked it, I got the right answer, more or less. So it was 10. Oh, that's why.
Yeah, I got
Because
the,
I said 10 meters, it's actually 10.64 meters. That's why it came out 10.6. Half wavelength at 14.1 megahertz. If you actually do the equation, it's 10.64 meters. Okay, that's the electrical length. Right?
Again, I just. I don't remember the equation and the 300 and the two, they're.
The 300 is the speed of light.
Yeah, speed of light divided by the frequency in megahertz gives you the length in meters. So if you divide 300 by 14.1, and I also put the 2 in for half a wavelength, because if I just divided it by 14, it'd be a full wavelength. So you get 10.64 meters. And then if you apply the 0.98 velocity factor, it cuts it down to 10.43. Their answer is 10.6, which is closer to this without the velocity factor. But nothing else is close. So it's got to be 10.6.
They're sure that 10.4.
Well, maybe they didn't include the velocity, but since they mentioned it's air insulated parallel, I don't know. Let's see, what is this? Non-resident doublet with parallel. I don't remember what all the first part was, but twin lead has characteristics of 300 ohms. Ladder line or window line is 450, and open wire feed line is 600. There's pictures of them. I have still have some of the twin lead. I have a bunch of window line. I don't have any ladder line. What's the nominal characteristic impedance of window line? Okay, and microstrip, we talked about that early on, where we're making a transmission line on a PC board. So what is microstrip? Okay, so we talked about characteristic impedance, foam dielectric versus solid, how frequency increases loss or attenuation, SWRs, matching networks, why we want to match, eighth wave, quarter wave, and half wave transmission line stubs, parallel conductors, velocity factor and dielectric. The physical length is always shorter than the electrical length. The different impedances for parallel lines and microstrip.